Welcome. Previous class I have discussed on the classifications of unit cells based on we said that I have also said that unit cell is the smallest unit of a complete crystal lattice which repeats again and again, that will form a complete crystal lattice. Okay, so these unit cells I have classified. This unit cell I have classified on the basis of one basis each, on the basis of locations of lattice points. There I say that these are that one is primitive, another I say that is non-primitive, and this primitive case that will be SCC, and in case of non-primitive we have that FCC, we have that BCC, and we have that FCC, BCC, and other like in-centered and edge-centered cubic lattice. Okay, so that we have discussed in the previous class. And other case that is on the basis of axial length, and that is interfacial angles. So on these two bases I have discussed in the previous class that this on this basis we have the primitive and non-primitive unit cells, and on this base we have that unit cells like cubic unit cell, and we have that unit cells that is tetragonal unit cells, and we have the unit cells that is orthorhombic, and we have that unit cells that is triclinic, monoclinic, past monoclinic, and we have the unit cells of triclinic, and we have the unit cells that is hexagonal, and we have the unit cell that is rhombohedrous. So this I have discussed in the previous class, that unit cell that is classified based on the basis of locations of the lattice point and on the basis of axial length and interfacial angles. And in this, throughout this solid state chapters, we will study the unit cells only that cubic unit cell types. Okay, we will not study that unit cells that is tetragonal, orthogonal. This we will not study. We will study only this type of unit cells. Okay, and for that locations on the basis of the locations of lattice point, we will study both primitive unit cells and non-primitive unit cells. Okay, so now we will discuss. So lattice point we will only talk about of cubic for unit cell we will talk only about of cubic unit cells. Okay, so let's say this is cubic unit cells, this is cubic unit cells. So you know that for cube all sides are equal. Okay, and for cubit also all sides are equal. So you know that that is square. This is the after a square 3 dimensions that will form a cube. So there all sides are equal. Like we see that for a square all sides are equal. So here also all sides are equal. Okay, so now I write length of all cube are same. Let's say that is A. Okay, so if it is A, then all are be A. And also what we know that for this cube, if we study about of this and this is the base diagonals. These are the base diagonals. okay, because this is base. So above these are base diagonals, so these are the base. Okay, so these are base diagonals. So how many base diagonals are there? So how many pairs? So one pairs they have the two diagonals, two pairs diagonals. So how many spaces are there? That is 1, 2, 3, 4, 5, 6. So 6 pairs means 12 pairs diagonals are present. Okay. So I'm not going on that. Whatever needed for us, that I'm going to discuss. That what is that this pairs diagonals value means. Let this is A and this is also A, because all the lengths of A cube are equal, so this is A. So now calculate that length of this base diagonals. How will you calculate? So you see that, let's say this is A, let's say this is B, and let's say it is C. So this is a right angle triangle because this is 90 degree. Okay, so for a right angle triangle that is ABC, but you see that AB square plus BC square is equal to hypotenuse, that is AC square. Okay, now this AB square is A, so this is going to be A square, and this BC is equal to A, so that for BC then that is equal to A square, then that is equal to AC square. So this is add, then this is 2A square, this is AC square, and then this AC is going to becomes, that is root 2A, and this AC is the base diagonals, and that is going to be equal to root 2A. Okay, similarly another we need in our in this topic, that is that body diagonals. So how will you calculate the body diagonals? So body diagonals are these points and these points, which is not base diagonals. You see, this is not a base diagonals for anything. So this is the body diagonals. Okay, so how you calculate this length of the body diagonals? So if you see that, if you take that this, if you take this and this is one of the right angle triangles. Okay, so this is the one of the right angle triangles. What is, let's say this is AC, let's say this is D. Okay, so for a right angle triangle that is ACD, what you see that this is for that hypotenuse. So this plus this is equal to this, that is AD square plus AC square, that is going to be the CD square. Okay, and now this AD square, this is AD square, this is the length, that is A. So AD square become A square. Now this AC square, this we see that this is that base diagonal. This AC is equal to base diagonal. It means AC square I will write root 2A whole square, that is going to be get CD square. It means this is A square and this is going to be the 2A square and this is going to be the CD square. It means that 3A square, that is going to be the CD square. So CD, this is equal to body diagonals, and that is going to becomes how much? Root 3A. So from here we understand that if that is a base diagonals, that value is root 2A, and body diagonals, that is root 3A, and A is, and that length of a cube is A. Okay, so this we have to always remember or memorize it, or we can calculate it, but it's better to memorize because you will use this one again and again, so no need to calculate, and it is also very easy to memorize. So base diagonals, that is smaller, so that is root 2A, and body diagonals, that is bigger than base diagonal, so that is root 3a. Okay, so root 2a and root 3a. So if you memorize it, so that we can solve the problems quickly, no need to have to calculate again and again. Okay, so just remember base diagonal root 2a, body diagonal root 3a. Okay, now we will going to this is so in solid state we will only study the unit cells, that is cubic unit cells. We will not study that orthorhombic, tetragonals, tricubic, that type of unit cell we will not study. We will only study that cubic unit cells. Okay, so you should know that about of this, his base diagonals, its body diagonals, what is the values. Okay, now we will talk about of that, let's say any base diagonals, sorry, any cubic centers. I will the cubic unit cells. This is cubic unit cells. So for this we say that length of a cube is, let's say a, then all lengths are will be a. Now so whatever we seen that whenever you do any lattice points, this lattice points actually we are drawing, this is a lattice point, this is lattice point, this is lattice points, all the corner lattice points are present. Actually we are drawing simply like this. Actually how it is exist, this is that this lattice points, they actually they all are touch with each other. Let's say that actually how it is exist. Let's say if you draw one lattice points here, then this lattice point is like this. Okay, and this lattice point, they are touch with each other. Okay, they are in contact, means this and this they have the touch, this lattice points are touch like that here, then this lattice point will be touch with this. Okay, so I'm not doing that. Whenever you see that exact picture, then these lattice points are all are they are touching with each others. Okay, so that's how that lattice points is present in a unit cells. So now what we are going to discuss is, we know that the relationship between, we will discuss on the relationship between that is the length of unit cells, that is we say that a, and radius of lattice points, radius of lattice point, that we say that r, that radius means this one. Okay, this is the radius, this is the radius for this. And note that all these lattice points have same side, it means same radius. Okay, so even if I drawing that from my, if I draw, then sometimes I draw that some is bigger, some is smaller, but actually that all the lattice points have the same side and radius also same. Okay, so all the radius are same, that should be keep in mind. Now a relationship between the length of unit cells A and the radius of the lattice points, and that is another is neighboring, or you can say that is interionic distance. Interionic distance, or this is also we can say interionic distance, or this is that atoms or I say that distance between centers of closest lattice points. Okay, that we say that D. So let's say this is that R, and that D is that the distance between the centers of closest lattice points. Okay, so distance between the centers of the nearest lattice point. So this and these are the nearest lattice points. So in between their centers, what is the distance? That is called the D. Okay, so these the centers between the any two nearest lattice points. So this is the two nearest lattice point, and this is their center. So this distance is called the D. Okay. So now we'll calculate that relationship between this A and R and D. Okay, so now I will draw another okay, so this picture, now we say that A is that length of the unit cells, length of unit cell, and so we are calculating the relationship between A and that is R and D. Okay, so where R is radius of lattice points, or sometimes it says that lattice point, or sometimes it says that atoms, or sometimes it says that ions. Okay, this lattice point sometimes called atoms, sometimes it's called also ions. Okay, and D is distance between the centers of any nearest lattice point. Okay, that is distance between centers of nearest lattice points, that is called D. Now how will you calculate the relationship between? So for that we will look that for different cases. For SCC, the relationship between this A, R and D is different. For BCC, the relationship is different. For FCC, the relationship is different. So first, if I look for SCC, that is simple cubic unit cell crystal. Therefore, this case, how we say that here that lattice points are present at the corners, only at corners. So draw that lattice point all at the corners, and we know that lattice points, they are touch with each other. So if I draw here like this, then another is like the touching. Okay, so this is the lattice point present in this unit cells. Now we will calculate the relationship between A, R and D. Okay, so what we see that this distance, this length of everywhere, that is A, this is A, so this is also A, this distance is A. Okay, and that is D is the nearest, that is the nearest that is distance between the center of nearest lattice point. So this is R and this is R. Okay, these two are, so A that is equal to, this is the 2R. Okay, and that D is the distance between the centers of that two nearest lattice points. So that is going to be also same as D. Okay, so here that for SCC, the relationship between A, R and D is A equal to 2R equal to D. Okay, this we have to remember, or we can easily calculate. Okay, and note for every case, for it may be SCC, it may be FCC, or it can be BCC. For all the case, this D is always 2R. This is always. Why I am saying that? Because what we say that this D is the distance between the center of nearest lattice points. So this is the distance between the centers of two nearest lattice point, two nearest two. Okay. So since it said that two lattice points, so in between two lattice points only 2R is possible, because whenever you are saying that if you are taking the two lattice points, so two lattice point, the shortest distance, that is always the 2R. It means this D is always equal to 2R. Okay, so either it may be SCC, FCC, or BCC. A is always 2R. Sorry, D is always 2R. Okay. So for SCC, A equal to 2R equal to DR. This you have to remember. Okay. Now for BCC, we will look for FCC, or let's look for BCC. For BCC case, again draw that structure, that is okay. Now BCC, what are there? Lattice points at all corners plus at body center. Okay, so lattice point is there at all the corners. So I will draw here all corners they have with that body center. Okay, so let's say draw like this. Okay, and another is like this. So here that all the corners they have with that one body center. So in this case, so here that first we will say we are doing that relationship between A, R and D. So for this case, we see that this is a body diagonals from here to here. This is a body diagonals. Okay, so this body diagonals, this is a body diagonals, and body diagonals we know that body diagonal is root 3a. Okay, and this root 3a, this is equal to how much? Let's say this from here to here, this is R, and here to here, this is again R, and this here to here again R, and here to here again R. So root 3a is equal to 4R. Okay, and we know that D is always 2R. Okay, because D is the nearest distance between two lattice points. So this is the these are two lattice points, and the centers distance between the centers. So for these two lattice points, the distance between the center is R and R, that is 2R. So D is always 2R, either it may be BCC, FCC, or SCC. Okay, so this is the relationship. Okay, now if I draw this, then what I'll do, root 3a equal to 4R, and that is equal to, this is 2R, then this is 2D, then this is again going to be 4R, so this is equal to 2D. So this is the relationship between A, R and D for BCC. Okay, now we will go for FCC case. FCC also, first draw that with lattice. So now that that is FCC, that what let's say lattice points present all corner plus body base center. So let's say this is the base. So in this base center one uh, lattice point is present and all the corners it is present. Okay, so if you draw that lattice points here, then one will be like this, another will be like this, and this is the at base center. Okay, these are the lattice points. So now calculate the relationship between A, R and D. So we see that this is the base diagonal. Okay, that's why I calculate that body diagonal and base diagonals. So base diagonal is root 2a, body diagonal is root 3a, and base diagonal is root 2a. Base diagonal is smaller and body diagonal is more, that is root 3a, and this is root 2a. Okay, so this root 2a is equal to, calculate how many are, 1 r, 1 r, this is 1 r, and this is 1 r. Total is 4 r. That is going to be 4 r, and we know that for all case d is equal to 2r. Okay, it means that 2d equal to 4r. So if you put here, then root 2a equal to 4r equal to 2d. So this is the relationship between a and r and d for FCC. Okay, so this relationship we have to memorize it, or you should know that is very easy to memorize. Why? Because for base diagonal, that is root 2a, and that is equal to 4r, and that is 2d, and body diagonals, that is root 3a equal to 4r, that is equal to 2d. So this will be remain same, only base diagonal root 2a and body diagonals root 3a equal to 4r equal to 2d. This is for BCC. Okay, so this will be the same as it is here. This will be the for BCC root 3a, for FCC root 2a. Okay, that's we see that. So we will remember that for SCC, that is always D equal to 2R equal to A. This is for SCC, and for BCC, that is BCC means root 3. BCC means body center, that is body diagonal root 3A equal to 4R equal to 2D. Okay, this 4R and 2D. And for FCC, this is base center, base diagonals, that is root 2A, and that is equal to 4R, and that is equal to 2D. Okay, so remember that if it is SCC, then D equal to 2R, and that is equal to A. Okay, and if it is BCC, then that is body diagonal, that is root 3A. FCC, that is base diagonal, that is root 2A, and this is 4R and 2D. And this we can easily remember, that is D is always 2R, and here we are talking about 2D, so this is going to be 4R. Okay, 4D equal to 2D and 4D equal to 2D. So this we have to memorize it. And for SCC, that is D equal to 2R equal to A. Okay, or that you should know that D is always 2R. This is always. Okay, so here D is equal to A, but for this case, these things. Okay, now we will discuss the next topic, that is packing fractions. The topic is packing fractions, or sometimes it is called that packing factor, and it is represented by P. Okay, so how we will calculate the packing fractions and packing factor? So what actually this packing fractions and packing factor is? Let's say this is fractions. Fractions is what you understand. Suppose we have that 100 marks, okay, and we give the exams and you get, let's say, 80 marks, then this is 80 upon 100. This is the fractions. Similarly, where this packing fractions is that in a unit cells is there. Unit cell is a complete unit cells. Okay, let's say cubic unit cell is there, complete cubic unit cell is there. On that, how many a number of lattice points you have, you that unit cells, how many number of lattice points are present? Okay, we have number of lattice points present in a unit cell, that is called the packing frequency. So if you define it, then number of lattice points presents for unit cells called packing frequency, called packing fractions, and that is represented by P. Okay, now this also you can write P is equal to number of total volume of unit cells, lattice points presents upon volume of unit cell. Okay, so this is actually we explain in terms of volume. So number of lattice points, number of we can say that number of volume of lattice point present for one volume, or we can simply say that number of lattice points present for unit cells. So this mathematically we say that total volume of lattice point presents upon volume of unit cells. Okay, now that percentage of packing frequencies, on that time this is going to be the total number of total volume of lattice points upon volume of unit cells into 100. Okay, so this one we can explain that packing frequency, or this is always, this P means we that we assume that that is in percentage. Okay, so this packing fractions, the total volume of lattice point. So what we say that first we will do that number of lattice point into volume of one lattice point, because total volume of lattice point, that I can say that number of lattice points into volume of one lattice point upon volume of unit cell. And in previous class I have said that total number of lattice point, how you calculate number of lattice points, that is represented as Z, that we used to calculate that total number of lattice point into contributions. That way we can calculate this number of lattice points. So total lattice total lattice points total lattice point into their contributions. So that is equal to Z. Okay, and say for SCC, then total number of lattice point, how many, that is only present at corners, that is 8, and contribution is 1 upon 8. Okay, so that is going to be get 1. Okay, that we will discuss. So here that P is equal to total number of lattice point, that we say in that is equal to Z into volume of one lattice point. So this lattice point is in a spherical, so its volume of a sphere is 4 upon 3 pi r cube. So this is going to be 4 upon 3 pi r cube, and volume of unit cells, that is, this is a cube, because you are talking only about a cubic unit cell, that is cube, so volume will be a cube. Okay, so here we see that this, okay, this is a cube, so cube is volume is a cube, and these lattice points are spherical, so they have that volume is 4 upon 3 pi r cube. Okay, that's what I did here. So this is the packing frequency to calculate, so that if we simplified it, then we will get that z into 4 upon 3 into pi, this r and a, so I'll write r upon a whole cube. Okay, so this is the simplified form of calculating the packing fractions. Now we will look for SCC, what is the packing fractions, and for BCC and for FCC. Okay, so we will look here for SCC, the packing fractions, and you will look for BCC, what is the packing fractions, and you will look for FCC, what is the packing fractions. Okay, the formula is for all these things, the common formula, that is, I am writing here, P is equal to Z into 4 upon 3 pi into R upon A whole cube. So use this formula to calculate the packing frequencies for this and this and this. So this Z, this is total number of lattice point. For SCC, that is always in the corners. So 8 into contribution is 1 upon 8, that is going to get 8 into 1 upon 8, that is going to get 1. So this Z for SCC, Z is 1, and for BCC, Z is equal to, that is corners plus body center 1, and contribution also 1. This is going to be 1 plus 1, that is going to be 2. So for this case, this value is 2, and for this case, that is, first is corners plus face center. How many face are 6, and contribution is half, so this is 1, this is going to be 3, so that is going to be 4. So for this is going to be 4. Okay, so now use this formula for this and this. So here that packing frequency will be Z is 1 into 4 upon 3. Okay, and this pi is 3.14 into R upon A whole cube. Okay, for this case, this will be that this is 2 into 4 upon 3 into 3.14 here R upon A whole cube. For this case, again, that is 4 into 4 upon 3 into 3.14 R upon A whole cube. Okay, now we know that for this case, for SCC, we say that is A equal to, here A equal to D equal to 2R, that relationship that we have seen, A equal to D equal to R, that we have seen here, A equal to D equal to 2R. Okay, so that's I write here A equal to D equal to 2R, and this case BCC means body diagonals root 3A equal to, that will be 4R equal to 2D. Okay, here 4R and 2D. Okay, here just multiply by 2 and 2, that is 4R, and this is going to be 2D. Okay, in this case, this is face diagonal, that is root 2A equal to 4R equal to 2D. So now it asking the relationship between R and A. Okay, so from here R and A, this is A equal to 2R, so R upon A, that is going to be So R upon A is going to be 1 upon 2. Okay, because we are taking this to this side and this, that is going to 1 upon 2. So here taking frequency is equal to 1 into 4 upon 3, 4 upon 3 into 3.14. Okay, and R is how much? We get R is A equal to R upon A equal to 1 upon 2. Okay, that is going to be R upon A is equal to 1 upon 2 this whole cube. Okay, similarly for this case 2 into 4 upon 3 into 3.14 R upon A. For this case this, so R and A, the relationship will be, let's say this is root 3A equal to 4R. So take this A to here, R upon A, that will be root 3 upon 4. So R upon A is root 3 upon 4, and this is whole cube. Okay, similarly for FCC, that is root 2A upon 4R. So this is root 2A equal to 4R. So R upon A is equal to root 2 upon 4. So just write that, that is equal to 4 into 4 upon 3 into 3.14, and that value is root 2 upon 4 whole cube. Okay, so likewise if you calculate these values, then we will get that this is about 52.3 percentage. Okay, so just calculate into make that into 100. Okay, packing frequencies with 100, here also with 100, here also with 100. So this is going to be 52.3 percentage for SCC case. Okay, and this here, if you calculate it, just multiply it, then we will get that this is going to be nearly 67.7 percentage, and approximately that is written that 70 percentage. Okay, so if it is written this one also fine, this one also fine. Okay, and that for FCC, in this case there is the highest packing frequencies we got, that is, if you multiplied it, we get that is nearly 74 percentage. Okay, that is 74 percentage, and it shows that highest packing frequency, because this is 70, this is 52.3, and this got the 74 percentage. So this is the highest packing fractions. Okay, for FCC. And note that we may get confused in the exam. If in exam given that packing frequency of HCP, or it may ask that CCP, on that case what is the packing fractions? So we have not studied the packing fractions of HCP and CCP, but we have studied these three cases only. These three cases we have studied, that is SCC, BCC and FCC, but we have not studied this HCP and CCP. Okay, so we may think that we leave it, but note that this SCP and HCP, this has that same packing fractions as that FCC, means packing fractions of HCP equal to CCP equal to FCC, that is equal to 74 percentage. So whenever it asks, it says that HCP or CCP or FCC, they have that same packing fractions, that is 74 percentage. Okay, this SCP means hexagonal close packing, and this CCP means cubic close packing, and this FCC means Okay, FCC means that we know that simple cubic lattice. This is S diagonal cubic crystals. This is S diagonal cubic crystal. Okay, so these all have that same packing fractions, that is 72%. So whenever it asks for HCP and CCP, then always assume that this is the FCC and its packing frequency is 74%. Okay, so this is the for the case of 3D. 3D, all are in 3D. Okay, this is also in 3D, this is also in 3D, this is also in 3D, and this is also in 3D. Okay, now I will give quick little bit some points on HCP and some points of CCP. Okay, what do you mean by HCP and what do you mean by CCP? So this is we say that this is hexagonal close packing and this is cubic close packing. How it is actually, so if you talk about of its one dimensions and also its one dimensions, then what we see here, let's say this is the one dimensions. Okay, and two dimensions, but from two dimensions we get the differentiate. Okay, for this case, for this is the CCP, HCP, and this is the CCP. Okay, for HCP, what we see that this and this next lattice point will be not here, that will comes to this point. These points, these points, these points, and these points, and another will comes another will comes to these points. Okay, not here, this point means in these points. Okay, and another will comes again to these points. This is the cases of HCP case, but whenever we talk about a CCP case, then this, so here another will comes not here, that will comes to here for the CCP case. Okay, another also the same case here. Okay, another also same case here. Okay, for this case it will be like this, in this corners it will come. So okay, let's say I'm doing another one. Okay, so whenever you see that let's say if I talk about of these lattice points, let's say I'm talking about of this lattice points, how many it joined to this lattice points. So this lattice point has joined with this one, directly touch, it touch with this one. Okay, and it is also directly touch with this one, but it not directly touch with this one. Okay, so it directly touch with this one, it also directly touch with this one. So how many it directly touch? That is 4. So here say that coordination number or we say that Cn of this lattice point is equal to 4 because it is touch with the 4 lattice points. Okay, so for this is the for case of CCP, and for the case of HCP, what you said, let's talk about of this. I can draw in the above side also. Let's okay, another is in these points. Right. For this case, okay, for this case, I'm talking about of these lattice points. Then how many to the lattice it joined directly touch? From here it directly touch with this, it also 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 directly touch with this. So how many lattice point? This lattice point has directly touch. So this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So for coordination number, that is Cn, for hexagonal, that is SCP case, this is equal to 6. Means how many lattice point it has touched directly, that is 6. Okay, so this is the about of 2D. And now whenever I'm talking about of this packing fractions of HCP, CCP, this is about of 3D. So in 3D case, it has the packing frequency equal to that FCC, that is equal to 74%. Okay, this I give just about of this introductions part. This is about just about of some knowledge about of CCP and HCP, how it is. Okay, now we will move to the last topic for today class, that is density. Okay, the last topic for today class, it is on the topic on density. So give my picture. So last topic for today class, that is on density. So what do you mean by density? Density. So density, whenever you talk that here, the density means that a density is, that is mass upon volume. That is the general formula for density. And for density of a crystal, cubic crystals. Now here we are talking about of density of cubic crystal. For this case, so the density will be is equal to that total mass of lattice points present upon volume of the unit cell. Okay, this is the density for a cubic crystal, density of cubic crystal, or you can say that density of cubic unit cell, because in that solid state we are only studying that unit cells, that is only that cubic unit cells. Okay, so for that density of cubic unit cell, that is total mass of lattice points present in the unit cells upon volume of the unit cells. Okay, so total mass. So here what we say that I will say that total number of lattice points present into mass of one unit cells. So one lattice points. Is it fine? Because this one I can write like this: the total number of lattice point present upon mass of one unit cells, one lattice point. Okay, upon volume of the unit cell. So now this value is going to total number of lattice points present. So that we explain by the help of Z, because Z is that number of lattice point present into contributions, that is equal to Z, because Z we say that number of lattice points into contributions. Like we say that SCC case it is uh, 1, and this Z SCC case Z equal to 1, and FCC case this Z equal to 4, and BCC case this Z is equal to 2. Okay, so this Z into mass of one lattice points, mass of one lattice point upon volume of the unit cell. So from here what we say that we know 6.022 into 10 to the power 23. So mass of one lattice point is we cannot calculate. So what we will do that we know that 6.02 into 10 to the 23 lattice points or particles lattice point have the mass equal to molar mass. Okay, so 6.0022 into 10 to the power 23 lattice point have the mass that is equal to molar mass of lattice point. Okay, because we see that let's say if a carbon, so 6.022 into 23 number of carbon atoms has the mass number is equal to that molar mass, that is 12. That is equal to 12. So from here I can write that 6.002 into 10 to the power 23 lattice point has equal to molar mass of the lattice point. So this I can write as molar mass is represented as capital M, and this we represented as Na. Okay, so because Na is equal to 6.022 into 23 or 23 particles. So instead of writing this we write simply Na, and molar mass we represented as M. So now this density, so we can write as Z into, okay, so this is for Na lattice points as M. Na lattice point has this, then or we can say I can write 6.022 into 10 to the power 23 lattice point has molar mass as M equal to this molar mass, then one lattice, then the mass of 6.0 into 10 to lattice point has mass equal to this. Okay, so then one lattice points, or you can say that mass of one lattice point is equal to molar mass upon, and this number of this will get divided into 6.0 to 10 to the power 23. So this I can write here. So mass of one lattice point, that is molar mass, I can represent by capital M, and this we can write as Na. So if I put this here, then I can write, so here we say that this density is equal to Z into mass of one lattice point upon volume of the unit cells. What you see here, D is Z into mass of one lattice points on volume of unit cell. So from here, this density, this what we have written here, Z into mass of one lattice point. So this is, so the mass of one lattice point equal to M upon Na. So that we write here, this is Z and this is equal to M upon Na. Okay, and volume of unit cell, because unit cell is cubic, unit cell is cube, so cube, volume of cube is AQ. Okay, so from here we can write that D, that is density, is equal to Z into M Na into AQ. This is the density of uh, cubic lattice cubic unit cell. Density of cubic unit cell, that is Z into M upon Na into AQ. Okay, so this one also you can remember as Jamna, that is Z M upon Na. Okay, so this is the density of a cubic unit cell. So now for SCC case, what is the density? So SCC case, Z is equal to that is 1, so that is equal to 1, and this molar mass, whatever that cubic unit cell given, that molar mass will given, so that will put here, that Na is always that 6.0 into 10 to the power 23, that will write here, and AQ, that is volume of that unit cells given, that we write, then we will get that mass for SCC. And for BCC case, this is going to be 2, so density is equal to 2 into molar mass upon Na into AQ. And for FCC case, that is going, density is going to be 4 into M Na into AQ. Okay, in this way we can calculate the density for SCC, BCC and FCC. Okay, so today up to this, we will discuss more in the next class. Thank you.